Hello everyone, I'm going to go over question 8 from section 4.6 on exponential logarithmic models. What we have is a classic scenario where we have a bacteria culture and we know how much is there after so much time, and then we check it later and we can see how much it's grown. Then we're given a bunch of different questions off of that. I'm going to go back and forth throughout this video because it's going to take a little while to answer each of these pieces. The first of which is, what is the initial size of the culture? So let's go ahead and look at this first. What we're dealing with is an exponential growth function. So it operates on this ab to the x, where you know b is greater than 1. And in this case, what's happening is our inputs are going to be our units of time. So for example, when it says after 20 minutes there's 400 bacteria cultures in there right here. That's what it means when x is 20. Our result, our f of x, is 400. If we look at this second piece here, we look at it at 35 minutes. Well, that means that at 35 minutes, our culture has grown to 1,500. So these are our inputs and outputs, right? You can think of it as like these are, let's say, x's and f of x's, like this. that's how our functional relationship is working here. It's important that we understand conceptually what's happening with it. So, for example, if I wanted to put 20 into this, well, what that means is I'm going to replace x with 20. And the result, what this thing will go to, the result of f of 20 is 400, like this. Or if we were to go again at 35, this would be ab now instead to the 35 equals 1,500. So we know our input, we know our output with it. And the important thing is both of these instances have a unique value for A and a unique value for B, where A is our initial and B is our growth rate. How fast is this thing growing along? Well, if we were to find these things, this is the information we're working with. Let's start with this part here. Now, we don't necessarily know a way to find A and B off of just this information, but we could isolate a variable. We could say divide both sides by that b to the 20th, and that would give us a value for A, right? So we would know what this is. We could do the same thing for other instance here. We could divide both sides by that b to the 35th. And then that same A is now isolated with it. So we know that these have to be equal. They both equal A. So our initial value, this A, equals both 400 over b to the 20th, as well as it equals 1,500 over b to the 35th there. And what's nice about this is we can actually solve this, right? So if we were to take this another step, we have enough information to calculate now what our value of b is. We could say multiply that b to the 35th over, and what that does is it makes it so we have b to the 35th over b to the 20th. That gives us, say, b to the 15th left over, right? Or if we have that 400, b to the 15th equals 1,500 there. We could solve this for b now. We can see that we're kind of getting through the tricky part of the problem. We can find it. This may be the next step that would be challenging. How do we isolate this? Well, if it was b squared, we take the square root. B cubed, we take the cube root. Same story. If we want to solve this, then what we need to do is take the 15th root of both sides. And you can find it, at least in Desmos, if you bring up your operations and click on functions here. If you are doing it on your phone, then you just click on that functions button and you'll see this same string of tabs that I have up in front of Desmos. And we want to click over here to miscellaneous, and we want to choose this nth root option, where what we want is the 15th root of this 1,500 over 400. So hopefully, at no point in this scenario did it seem clear that like, oh, this is going to be some nice number. It's not, right? So this 1,500 over 400, that's not a nice number. We could reduce this a little bit, right? We could divide both the top and bottom by 100 and get that, but it's not going to get much nicer than that. So we know what our growth rate is, right? We know that, say, in this scenario here, so let me copy this. We go all the way back to the beginning. This a times b to the x, this is going to be what my b is. So that shows me what my growth rate is. Is it a nice number? No. No, again, not at all. We've got this 1.092. If we threw that into context, what that means is for every unit of time, we're going to be growing by about 9.2%, right? Or how it compares to the last one is it's 109.2% from whatever it was previously. So it gives us that part of it. And we have this set up so that way we can figure out what A is as well. We could come back here, and since we've defined what B is, Cosmos is doing the work for me, but I could plug in B into this, and it tells me what A is as well. So in this case, A is this 68.657 thing, or it's a little more than 68 and a half cultures of it, right? So you could use that amount for it. So if we go to the doubling period, actually I think what I'm going to do is I'm going to break this up into a series of videos. That's how you find that.